Okay, we're going to talk about application of exponents and exponential notation, and our first topic is on magnitude. So as we begin this discussion, you don't have to write any of this down. This is just some background information. So in addition to applications within mathematics, exponential notation is indispensable in science. It is used to clearly display the magnitude of measurement. That means how big or how small. We are going to explore this aspect of exponential notation in the next 7 lessons. Understanding magnitude demands an understanding of the integer powers of 10. Therefore, we begin with 2 fundamental facts about the integer powers of 10. What does it mean to say that 10 to the nth power for large positive integers n are big numbers, and that 10 to the negative nth power for large positive integers n are small numbers? Now you might be saying, why does this say large positive integers? Remember, this is n and then the opposite of n. So n can still be large positive integers. The fact that it has the minus sign in front of it means that we're going to take the opposite of that, and when we do that, the result is small numbers. Alright, so now you can start writing in your journal. We have our first fact. The numbers 10 to the nth power for arbitrarily large positive n, or integers that are n, are big numbers. Given a number m, capital M, no matter how big it is, there is a power of 10 that will exceed that number that we're going to represent by capital M. The other fact is the numbers 10 to the negative nth power for arbitrarily large positive integers n are small numbers. Given a positive number, capital S, no matter how small it is, there is a negative power of 10 that is smaller than S. Okay, so again, farther away from 0. Fact 2 is a consequence of Fact 1, so we're going to address Fact 1 first. The following 2 special cases illustrate why this is true. So on your lesson worksheet, highlight the keywords and important facts. Do this, which should be in your math journal also, but once you have highlighted the keywords and important facts on your lesson worksheet, then continue the video. Okay, let's take a look at example 1, which we're going to do in your journal. So, example 1, let M be the world population as of March 23rd, 2013. Approximately M is equal to 7,073,981,143. It has 10 digits, if you count those up. That would be 3, 6, 9, 10. And is therefore smaller than any whole number with 11 digits, such as 10 billion. If you notice, this is 10 billion, this is 7 billion. This has 11 digits. 3, 6, 9, 10, 11. But 10 billion is the same as 10 to the 10th power. Notice that we have 10 zeros here. It's a 1 with 10 zeros after it, so it's 10 to the 10th power. So M is less than 10 to the 10th power, meaning that the 10th power of 10 exceeds this number, which is M, obviously because it's 7 billion. Alright, let's take a look at example 2. Let M be the U.S. national debt on March 23rd, 2013. And that number M is 16,755,133,009,522 to the nearest dollar. And if you count these up, it has 14 digits. While the largest 14th digit number there is 99 trillion, so on and so forth. Therefore, M is less than 99 trillion, which is less than 100 trillion. And 100 trillion is 10 to the 14th power. And we know that by counting up the decimal places, 3, 6, 9, 12, 13, 14. It's 1 and 14 zeros. So that is the 14th power of 10 exceeds our digit m, which was 16 trillion. And again, 100 trillion definitely exceeds 16 trillion. All right, so with that, go ahead and complete exercises 1 and 2 on your lesson worksheet. And again, refer back to those 2 examples that you just wrote down in your math journal. And then once you're done with that, continue the video. Okay, so this is what you should have come up with for the answers to exercise 1 and 2. Again, if you have any questions about the explanations or the answers, make sure you write it down, highlight it, and bring it to class. All right, let's take a look at our next example, example 3. This example set is for the general case of fact 1. So here is case 1. Let m be a positive integer with n digits. So we don't know how many digits it is. It could be 5 digits, 6 digits, whatever. As we know, the integer with 99 or any amount of 9s, it doesn't matter how many 9s, is going to be greater than or equal to m. So if I said 47, that's 2 digits, well, 99 would be greater than 47 because it's the same number of digits, 2 9s. Therefore, a number with 1 and however many zeros, if it's the same number of zeros, is going to exceed m. So if we use the example I just gave, 47, that's 2 digits, 99 is 2 digits, and 100 would be 2 zeros. So that still exceeds m if m was 47 in this case. Well, since 10 to the nth power is 1 with however many zeros in it, then 10 to whatever power is always going to exceed whatever our number is, our integer, being that it's the same number of digits. So symbolically, we can say that m is going to be less than 99, or 9, however many 9 digits you have, and which is going to be less than 1 and however many zeros you're going to have. So therefore, an n-digit positive integer, which we are calling capital M, the nth power of 10 always exceeds m. Alright, so let's take a look at case 2. In case 1, m was a positive integer. For this case, let m be a non-integer. Okay, so that means if it's a non-integer, it's going to be a decimal. So we know m must lie between 2 consecutive points on a number line. For example, there is some integer n, so that m lies between n and n plus 1. In other words, n is going to be less than m, and if I add 1 to n, that's going to be greater than m. The example we can use is 45,572 and 384 thousandths. Well, that's going to be between 47,572 and 45,573. Okay, those are integers. M is our decimal because it falls between n and n plus 1. Consider the positive integer n plus 1. According to the reasoning above, there is a positive integer n, so that 10 to the nth power is going to be greater than n plus 1. So that is what's being shown right here. Even if you were to say this is 9, and if 9 plus 1 is 10, well, there's still a power of 10 that is going to be greater than 10. In this case, it would be 100. Since n plus 1 is greater than m, then again we have 10 to the nth power is got to be greater than m. So the same thing holds true. Consequently, for this number m, 10 to the nth power will exceed it. And therefore, we have now shown why fact 1 is correct. Whether it's a integer or a non-integer number, in this case a decimal, fact 1 is still true. There is always going to be a power of 10 that will be greater than m. Alright, exercise 3. On your lesson worksheet, you're going to complete exercise 3. Look at the previous examples to help you answer this question. And then once you're done with that, continue the video to check your work. So, let m be a positive integer. Explain how to find the smallest power of 10 that exceeds it. And again, based on the explanation from the examples, if m is a positive integer, then the power of 10 that exceeds it will be equal to the number of digits in m. For example, if m were a 10-digit number, then 10 to the 10th power would exceed m. If m is a positive number but not an integer, then the power of 10 that it would exceed it is the same power of 10 that would exceed the integer to the right of m on a number line. So, and then they give an example using 5,678 and 9/10, or you can pick whatever example you want. Alright, example 4. The average ant weighs about 3 10,000ths grams. So observe that this number is less than 1 and is very small. We want to express this number as a power of 10. We know that 10 to the 0th power is 1, so we need a power of 10 that is going to be less than 0. So based on our knowledge of decimals and fractions, we can write the weight of the ant as 3 10,000ths, 3 over 10,000, which is right here, which is the same as 3 over 10 to the 4th power. Our work with the laws of exponents taught us that 3 over 10 to the 4th power is the same as 3 times 1 over 10 to the 4th power, and 1 over 10 to the 4th power can be written as a power of 10 with a negative exponent. So it would be 3 times 10 to the negative 4th power. Therefore, we can express the weight of an average ant as 3 times 10 to the negative 4th power grams. Alright, here's another example. The mass of a neutron is, and I'm not even going to try to figure out how to say this, but you can see how many zeros there are, and then 16749 kilograms. So let's look at an approximated version of the mass of a neutron. In here we had 3, 6, 9, 12, 15, 18, 21, 24, 25, 26 zeros, and here we have the same thing with 26 zeros and a 1. So we've just looked at the approximate version. We've dropped the 6749. Well, we already know that 10 to the 4th, or the negative 4th power, takes us to a place value 4 digits to the right of the decimal point, which is the 10,000ths place. Well, we're going to need a power of 10 that would take us 27 places to the right of the decimal, which means that we can represent the simplified mass of a neutron as 10 to the negative 27th power. In general, numbers with a less value, or a value less than 1 but greater than 0, can be expressed using a negative power of 10. The closer a number is to 0, the smaller the power of 10 that will be needed to express it. So if you notice on a number line, the mass of a neutron, 10 to the negative 27th power, is less than the average weight of an ant, which is 10 to the 3rd power. So if we want to know which one is greater, then obviously the average weight of an ant is greater than the mass of a neutron. But notice the powers. The greater the negative power is, the smaller the number is. Okay? Alright, so exercise 4 through 6, you're going to answer these on your lesson worksheet. Before continuing, A hint when you answer question 5 or exercise 5, it might help to use a number line like in the previous example. Okay, go ahead and do that and then continue the video. Alright, so here are the answers to exercise 4, 5, and 6. Go ahead and check your answers and then continue on. Alright, that is it for our lesson for today, so let's go ahead and summarize. No matter what number is given, we can find the smallest power of 10 that exceeds that number. And very large numbers have a positive power of 10, which means we can use negative powers of 10 to represent very small numbers that are less than 1 but greater than 0. All right, we'll see you in class.